In this lesson, we'll be studying quadratic functions and their graphs. Let's start with the definition. A quadratic function is a second-degree polynomial function. So what that means right there is that the highest power will be 2. That can be written in this form. Now here a, b, and c are any real number and a is not 0. If a were 0, then you would have 0 times x squared, and so this whole term would just be 0, and then the highest power at that point would be degree 1, and then this would no longer be quadratic, it would be linear. Now, the graph of any quadratic function is a parabola, which is a U-shaped graph. We will study parabolas opening upward or downward. If a parabola is opening upward, then it has a lowest point called the minimum, and the minimum is located at the vertex of this parabola. So this point here would be called the vertex. If the parabola is opening downward, then it has a highest point called the maximum, and the maximum is located at the vertex. So we'll be studying these two different classifications for parabolas. Now this form is called standard form, also called vertex form in some textbooks. This form involves a perfect square in the variable x. Now you're going to see that if a function is written in this form, it is very, very, very convenient because it gives us so much important information regarding the graph of our function. Let me break it down for us now. Now, a is considered to be the leading coefficient. If that leading coefficient is positive, that means the direction of your parabola is upwards. If the leading coefficient a is negative, then the direction of your parabola is downward. So it's relatively easy to determine the direction of your parabola. All you got to do is look at the leading coefficient. Is it a positive number or a negative number? Now, if your parabola opens upward, that means it has a minimum or a lowest point, and it's located at the vertex. If the parabola opens downward, that means it has a maximum or a highest point on the graph, on the parabolic curve, and it's located at the vertex. Now, what's really cool about this form here, called standard form, is that it actually tells you what your vertex is. Your vertex will have the coordinates h, comma, k. Now, this is the whole benefit, the main benefit of this form, is that you get this probably most important point on the whole parabolic curve is the vertex, right? You get the vertex for free, really. All you got to do is locate what h is and what k is. Now, there's something called the Axis of Symmetry. The Axis of Symmetry, or AOS for short, is a vertical line that goes right through, that intersects your vertex. A vertical line that intersects your vertex, and what it does is it basically splits your parabola in half, and so that the left branch mirrors the right branch. Here, let me zoom in. Let me give you a picture of a parabola so you can see what I'm talking about. Here I drew a picture of a parabola opening upward. I could have made the same argument with a parabola opening downward. I'm going to show you what the AOS looks like. I'm going to use a dashed line to draw the AOS that's going right through my vertex. And what it does is it's a line of symmetry. And so this left branch here mirrors the right branch. The right branch mirrors the left branch. So it's as if this line of symmetry is like a mirror. And what you see on the left, you get its mirrored image on the right. And this will be true for all of our parabolas that we study. Now, because the axis of symmetry is a vertical line going right through your vertex, the equation that defines your AOS is x equal to h. A lot of times I tell my students, if you are successful in identifying your vertex, then your AOS just follows from that. It's always x equal to this first coordinate. All right, let's graph some parabolas. Let's graph some quadratic functions. Here we have f of x is equal to 2 times x minus 3 quantity squared minus 4. The first thing I would have us do is find the direction of this parabola. Is it opening up or down? Because the leading coefficient is positive, we do know that the parabola is going to be opening upward. The next thing I would have us find is the vertex and the AOS. Now remember, the vertex is h, comma, k. H, comma, k. So in this, for this function, your h value is positive 3 and your k value is negative 4. Now, I want you to be very careful when it comes to identifying the first coordinate of your vertex, which is 3 here, okay? Because I think it's dangerous to look at this and say, well, I see negative 3, right? Minus 3, so I'm going to put minus 3 here, which would be wrong. Let me scroll back up and show you standard form again. Now, standard form was here, and we said that the vertex is h, comma, k. Notice that your h value is the numerical value that follows the subtraction sign. We did not write negative h, we just wrote positive h, right? So it's the number that follows the subtraction sign. So in our example here, the number that follows the subtraction sign is 3. So I put a positive 3. Because of this, I always encourage students to write down the opposite of what they see when it comes to the first coordinate of your vertex. Whatever you see here, write down the opposite. You see minus 3, so put positive 3. Now your AOS is the vertical line, so it's x equal to, and it's going right through your vertex, so it's x equal to 3. Remember, it's always x equal to that coordinate. All right, now let's go to the x and y coordinate plane and plot what we have so far. The first thing I would like to do is to plot my vertex, positive 3, negative 4, maybe about right there. There's our vertex. The next thing I would like to do is to show you the AOS, which is x equal to 3, and always use a dashed line, please, when you're graphing your vertex. And I always use a dashed line because the AOS is not part of the graph, but it does help us get the final picture. This is all we have so far at the moment, everybody. And what I would like you to do now is to generate or find 2 additional points. Now, in theory, you can plug in whatever x value you want into your function, okay? Plug in whatever x value you want because the domain is going to be all real numbers. However, we want to work smart because, you know, if you plug in like, I don't know, 10 minus 3 is 7, and 7 squared is 49, and 49 times 2 is 98, you know, so things are going to get really large really quickly. So we should choose values for x to plug in here that keep this expression relatively small, so that it becomes a little easier to graph. So this is my rule of thumb. Let's choose an x value that is really close to your vertex or your AOS. This is x equal to 3 right here. So let's plug in either 2 or 4. Now you can plug in whatever you want, but this is my suggestion. Plug in 2 or 4. I'll go ahead and plug in 2. All right, I'm plugging in 2 into my function here for x, and I'm going to evaluate. So then this becomes 2 times negative 1 squared minus 4. Please follow the order of operations, so be very careful. And then you get negative 2. 2 minus 4 is negative 2. So the ordered pair is 2, comma, negative 2. Let me show you where that is. 2, comma, negative 2 is about right there. So we already have the left branch of my parabola, right? Now, the next point that I want you to get, because I want you to generate 2 additional points, I don't want you to plug in anything for the second point. I want you to take advantage of the symmetry. Because of this line of symmetry, the axis of symmetry, what you see on the left side must mirror what you see on the right. So watch this. If this point is on the graph of my parabola, and it is 1 unit away 1 unit away from the AOS. That means I should get another point that's 1 unit away on the opposite side of the AOS. So what is the mirrored image of this point with respect to the AOS? Well, if this point is 1 unit away, then I should get another point that's 1 unit away on the other side. So if 2, -2 is on the graph, then 4, -2 is also on the graph. So this is taking advantage of symmetry, right? And so I don't want you to have to plug in a different x value here. Please don't do that. Use symmetry instead. So in summary, we found this point by plugging in 2, and we got -2, right? We got that point. And then symmetry is what gave us the mirrored image, which is 4, -2. So this is our picture. This is just a sketch, right? All of these will be just sketches of our parabolas. Now, I want us to find the domain and the range for our graph, the domain and the range for our function. Now, let's not forget that the domain is the set of all your x values, and the way you read your domain is by reading your graph left to right. How far left is this going, and how far right is it going? Now, as you go further left, this parabola is getting wider and wider and wider, and if you zoomed out, you would see that this parabola continues going left forever. So it'll be from -infinity all the way to, and then it's also doing the same behavior on the right. It's getting wider and wider, going forever to the right. So the domain for this quadratic function is -infinity to +infinity. In words, you would say it's all real numbers. Now, the range is a set of your y values, and you read your range by reading the lowest point to the highest point, the lowest y value to the highest y value. The lowest point is here, it's the vertex, and the y value, we already wrote it down, the y value in the vertex was -4. So we're going to read the range from -4 all the way up to +infinity. So it'll be from -4 to +infinity. That's the range. You always put a bracket here because this value, this function value, is actually located on the curve. It's right here. So include it by putting a bracket. All right, let's look at another example of a quadratic function. All right, our new function is g of x is equal to -2 times x plus 1 quantity squared minus 3. Now, these are the three things I would ask you to find: direction, vertex, and AOS, right? And then when we're done, we'll find 2 additional points. Now, the leading coefficient in this example is negative, and because it's negative, we know that this parabola will be opening downward. Now, the vertex, we want to be very careful to identify the vertex properly. Now, you see a +1 here, therefore the vertex starts as -1. Remember to read the opposite. This is your h value. So it starts at -1, be careful there, comma, -3 there. So -1, -3. Now, the AOS is always a vertical line going through your vertex, so it's x equal to, and in this case, it's x equal to -1, x equal to that value. All right, let's go ahead and graph what we have so far. The first thing I like to graph or to plot is the vertex, so -1, -3, which is about right here, okay, -1, -3. And then I like to show my AOS, which is x equal to -1. Of course, going right through your vertex there, okay? This is what we have so far, everybody. What we want to do now is generate 2 additional points. Now, although you can plug in whatever you want for x, I want to plug in an x value that is close to my AOS. So in this case, -2 would be a good choice, or 0. I'm going to go with 0. All right, I'm going to plug in 0 into my function. All right, so I'm plugging it in, and I'm getting, let's see, -2 times 1 minus 3. So this is -5. Okay, let's go ahead and plot this point. The point is 0, -5, which is about right there, right on the y-axis. So that's a y-intercept, isn't it? Right on the y-axis. And so what we want to do now is find an additional point using symmetry. The mirrored image of this point would be right over here, wouldn't it? Now keep in mind, this point here, 0, -5, is just 1 unit away from your AOS. That means if you go 1 unit from your AOS on the opposite side, you get its mirrored image, which would be -2, -5. -2, -5. So about right there, okay? This is the mirrored image. And so now I can complete my graph. Now, it bothers me that this looks like a V. It's supposed to be a U shape, a parabola. So try your best to make it look like a U and not a V, okay? So -2, -5 is our point using symmetry. All right, we did it. Let's write down the domain and range. Now, the domain is read left to right, and it's a set of your x values. Now, how far left is this going? Well, the further low you go, the wider it's getting to the left, going forever to the left and forever to the right. So the domain, again, is all real numbers. This was the domain for the previous function. Now, I'll tell you this right now, that whenever you have a quadratic function, okay, whenever you have a quadratic function, the domain will always be all real numbers because these parabolas, whether they open upward or downward, they branch out indefinitely to the left and to the right. They get wider and wider, if you will. And so the domain will always be all real numbers for any of our quadratic functions that we study. Now the range, on the other hand, it's a set of your y values, and this is going to change, all right? So you read it from the bottom to the top. How low is this going? It's going low forever, right? So it's going from -infinity is the first thing I write, all the way to the highest point. The highest point is the vertex, and we already located the y value at this vertex is -3. So the highest point is -3. We call that the maximum. All right, very good, everybody. Now, what I want to walk you through is, what do I do when the function is not written in vertex or standard form? How do I get all of this information when the function is not written like this? Let's talk about that now. All right, so I just want to remind you what standard form looks like, okay? It has a perfect square in the variable x. Look at this function. It's not written in standard form. So how do we determine the direction, the vertex, and the AOS for the graph of this quadratic function? Well, this is our strategy. Let's complete the square in the variable x. If we are successful in completing the square in the variable x, then this function will be rewritten to be in standard form, and then we can easily see what our vertex is. Now, in order to complete the square, now we studied this in earlier lessons. In order to complete the square, your leading coefficient must be 1. And good news, it already is. The next thing you need to do is isolate your variable terms. Now, the way I'm going to isolate my variable terms is by just collecting them using the associative property of addition, right? So I collected them or isolated them by just using grouping symbols. I'm using parentheses. So now I'm ready to complete the square. So what I'll do here is, remember, we have to take half of the coefficient of the first degree term. So we know that we have to take half of 6, which is 3. And then we have to square 3, which is 9. 9 is the square that you're adding to your function. So I'm going to go ahead and add it right here. However, adding 9 units to your function will change your function, right? Now it's a different function altogether. In order to compensate for that, I will subtract 9 at the same time, so to try to keep the function exactly the same as the original function, right? Now, you know this is true because if you get rid of the parentheses here, 9 and -9 cancel out, and all you're left with is +5, which matches the original function. So whatever you add, you're going to have to subtract at the same time, right? To undo what you've done, to undo the change you've made. Now, this is a perfect square trinomial, so it factors as a square of a binomial. So then it factors like x plus 3 quantity squared. And then 5 minus 9 is -4. Now that this function is written in standard form, okay, this is standard form, you and I can answer the question, okay? Now, as far as the direction of this parabola, we could have answered that in the very beginning. The leading coefficient is +1. It still is +1, okay? But I'm just saying we knew the direction from the beginning. This parabola is opening upward. Sometimes if I don't say direction of the parabola, sometimes I say orientation. Is it opening upward or downward? By orientation, okay? Now the vertex, remember it's H, K. But be careful when you're identifying H. Take the opposite of what you see. So in this case, the vertex is -3, -4. The AOS is x equal to -3. All right, let's graph this function. F of x is equal to 2x squared minus 4x plus 5. Because the leading coefficient is positive, we know that this parabola opens upward. We have an upward opening parabola. All right, let's find the vertex. And the AOS, I guess. All right, so let's complete the square in x in order to rewrite this function in standard form. All right, here we go. The first thing I'm going to do is isolate my variable terms. My variable terms are 2x squared minus 4x, right? I'm going to isolate those. And I'm going to do that by just using the associative property of addition, putting some grouping symbols around those two variable terms. Now, before we complete the square, you and I know that the leading coefficient must be 1. The leading coefficient at the moment is 2. In order to get this leading coefficient to be 1, I'll just factor the 2 out. Now, I'm factoring the 2 out from each of these variable terms. So I get x squared minus 2x. Don't forget you have a plus 5 on the outside. Now your variable terms are isolated and the leading coefficient is 1. Now we can complete the square, okay? We take half of the coefficient of the first degree term. Now, the first degree term is right here. This is also the first degree term, but we're not looking at this anymore because it's been factored now like this. So the coefficient of the first degree term is no longer -4, it's -2. So take half of -2, which of course is -1, and then square -1, which is +1. This is the square that I'm adding to my function. Now, you must undo, at the same time, you must undo what you've done. Now, if I add 1 there, how do I undo that? How do I undo this addition of 1? Well, some of you may be thinking, well, if you're going to add 1, subtract 1. Not that straightforward here. Because the 1 is inside of this group and there's a 2 out front, you really added 2 times 1. You've really added 2 to your function. So then what you must do to undo that is subtract 2 at the same time. Now that's confusing, isn't it? Because I see +1, so I just want a -1. No, it's actually 2 times 1. You've added 2, so subtract 2 at the same time. Be careful with that. All right, so we have 2 times x minus 1 squared plus 3. Now this, ladies and gentlemen, is standard form for this quadratic function. Now I can see what my vertex is. My vertex is h, k. It is +1, +3. My AOS is x equal to 1. So this is what we have so far, everybody. Now let's generate some additional points. Now, I think it's safer to plug in values in the original function that was given to you and not the standard form of the function that you and I found, just in case we made a mistake. All right, so you know the rule of thumb. Let's plug in a value that is close to your AOS. 0 or 2 would be a good idea. If we plug in 2, though, we have a lot of arithmetic to do. Whereas if we plug in 0, we would have no arithmetic to do. because 0 squared is 0, 2 times 0 is 0, negative 4 times 0 is 0. So all of this would go away if you plug in 0, and you're left with just your constant term. F of 0 would just be 5, right? If you plug in 0, all of your variable terms go away. 0, 5, everybody, is the point that you and I just generated. Wait a minute. We just found the y-intercept. This is the y-intercept. Now, the point that you get for free, if you will, the mirrored image of 0, 5, would be 2, 5, using symmetry. So then this is my final picture. All right? Very good. Now remember that you always find a y-intercept whenever you let x be 0, okay? So finding a y-intercept, all you got to do is plug in x equal to 0, which is exactly what we did here. So if ever you're asked, find the y-intercept of the graph, just plug in x equal to 0. And when the function's written like this, that's fairly easy, because when you let x be 0, the variable terms are just 0, and you're just left with your constant. So what I'm saying is the constant term on the back end is always your y-intercept. Now be careful. I mean the constant term when it's written in this form. When you have standard form, you know, the vertex form, that's not what I'm talking about. I'm talking about the constant term when the function's written in this form. All right, let's look at another example. All right, for the last part of this lesson, I want to focus on the vertex formula. Now, we found the vertex just a minute ago by completing the square in x. Another way you can find the vertex for the parabola of a quadratic function is by using the vertex formula, negative b over 2a. Now, remember that when a function is quadratic, it's written of this form, right? Or can be written in this form. So all you have to do is figure out what negative b over 2a is. Now, don't forget, b is the coefficient of the first degree term, and a is your leading coefficient, okay? Whatever negative b over 2a turns out to be, whatever this number is, it's the first coordinate of your vertex. Then you take that number and plug it into your function to find the second coordinate of your vertex. So this is like h, comma, k. All right, let's find the vertex of the graph of this quadratic function, and let's see if we can use the vertex formula. All right, negative b over 2a. So negative b over 2a. Now be very careful, it's negative. And your b value, be careful here, your b value is negative 6, right? So it'll be negative 6 over 2 times a, 2 times a, which is 3. This is your a value right here. Now, you can see how you need to be careful with your signs, as always, right? Because you have a negative on the formula, and then your b value was negative as well. Negative, and then another negative, right? So just be careful. So those two negatives make a positive, and 6 divided by 6 is 1, okay? So this is already the first coordinate of your vertex. What I need to do now is plug in what I found for negative b over 2a. Plug in the number 1, right? So this here is the first coordinate of your vertex. In order to find the second coordinate of your vertex, I just take that expression, negative b over 2a, which turned out to be 1, and plug it into your function. So now you got 3 times 1 squared minus 6 times 1 plus 1, which just gives you negative 2. This here is the second coordinate of your vertex. So using the vertex formula, you and I found that the vertex, I'll just put v for vertex, is 1 comma negative 2. And I did not have to complete the square. Of course, I would have gotten the same vertex had I completed the square in x. But you can also use the vertex formula to find your vertex. All right, let's look at a couple more examples here. We want to graph this quadratic function. Negative 2x squared minus 8x minus 8. All right, we can see that this parabola is going to be opening downward. How so? Well, the leading coefficient is negative. So it's definitely a parabola opening downward. Now, in order to figure out the vertex, I'm going to use the vertex formula. So I'm going to do negative b over 2a. So it's negative 8 over 2 times negative 2. Now, there's a total of 3 negatives here, so the whole thing is negative. And 8 divided by 4 is 2. So the vertex starts as negative 2, comma, something. In order to figure out the second coordinate of my vertex, I'll plug negative 2 into my function. Man, you just have to be very careful with all these signs here. There's so many negatives. Okay, barely fit it. All right, so this is negative 2 times positive 4 plus 16 minus 8. So this is negative 8 plus 8, so this is 0. So the second coordinate of your vertex is 0. Now your axis of symmetry is x equal to negative 2. All right, everybody, this is all of the information that you and I would usually collect in the previous examples that we've looked at. I'm going to add a couple more steps here for us to follow. I want us to find the intercepts of the graph. Let's start with the easiest one to find, the Y-intercept. Now, I mentioned earlier how the Y-intercept is always going to be your constant term when it's written in this form. So you can see right now that the Y-intercept will be negative 8. Now, algebraically speaking, what you would do is you would plug in 0 for x in order to find your Y-intercept. So you'll see that both of these variable terms, if x is 0, both of these variable terms will turn to 0 and leave you with just negative 8. So I can write it like this. F of 0, if you plug 0 in for x, all you'll be left with is negative 8. So the Y-intercept is 0, comma, negative 8. Now, the part that is usually, more fun to find are the x-intercepts. Now, remember, to find x-intercepts, you let y be 0. Now, f of x notation represents y. So I'm going to let f of x be 0. I'm going to let y be 0. That basically means take your whole expression, set it equal to 0. So let me show you that. So I'll take negative 2x squared minus 8x minus 8 and set this whole thing equal to 0 and solve. So this is just solving a quadratic equation. If you solve this quadratic equation, you'll find the two x-intercepts. So the first thing I will do to help me solve this a little easier is by factoring out a negative 2. If I factor out a negative 2, then I have the following resulting trinomial, which factors, I got to move this up here, which factors as negative 2 times x plus 2 times x plus 2 equal to 0. What I'll do is I'll set each factor equal to 0 now and solve. So I'll set negative 2 equal to 0, I'll set x plus 2 equal to 0, and I'll set x plus 2 equal to 0. Now, it's a little silly to set the constant factor equal to 0 because negative 2 is not 0, so that just goes away. Another thing that is a little silly is to set each of these factors equal to 0 because they're the same factor. I mean, you should set each variable factor equal to 0, don't get me wrong, but they're the same exact factor, so you're going to get the same solution twice. So don't do it twice, right? Just take one copy, if you will, and set that one copy equal to 0 and then solve. So you're getting x is equal to negative 2 after subtracting 2 from both sides. So your x-intercept actually happens to just be 1. What I mean is just one x-intercept, not 2. So your x-intercept is negative 2, 0. All right, let's go to the x and y coordinate plane and plot everything we have. Okay, everybody, this is what we have so far. Here's our vertex, which is also our x-intercept. Here's our y-intercept, our axis of symmetry, and we know that this parabola opens downward. So the right branch behaves like this. Now let's find an additional point using symmetry. Now remember how this works. This point here, the y-intercept, is 2 units away from the AOS. Look at it. That's 2 units away from the AOS. That means its mirrored image would be on the opposite side of the AOS, also 2 units away. So then what would then be the mirrored image of 0, negative 8? Negative 4, negative 8. That's right. This point here is being found by using symmetry. -4, -8. All right, everybody? Very good. Let's get the domain and the range for our graph. Now, don't forget the domain will always be all real numbers, right? Because these parabolas get infinitely wide, right? They go to the left and to the right indefinitely. But the range is read from the bottom to the top. How low does this parabola go? So negative infinity would be where you start. And then how high does it go? Now be careful, your range is a set of your y values. So don't say that the highest y value is -2. That would be wrong. -2 is the x value at this location. The y value at this location is 0. So you would say 0 is your highest y value. All right, one more example here. F of x is equal to -2x squared plus 12x minus 16. All right, this is a list of most of the information that we'll gather. The direction, vertex, AOS, Y-intercept, and X-intercepts. We'll also find an additional point using symmetry when we're done, or toward the end. All right, this is a great place to pause the lesson and to try this information out on your own. All right, so the leading coefficient is negative, so therefore the direction of this parabola is downward, okay? The vertex, I'll find the vertex by using the vertex formula as opposed to completing the square. So I need to do negative b over 2a, so it'll be negative positive 12 over 2 times -2. So this is a positive number, and it is 3. So the vertex is 3 comma something. What I need to do now is plug 3 into my function. So I'm plugging 3 into my function, and I am getting the following, which gives me 2. So then the vertex is 3 comma 2. All right, cool deal. The AOS is x equal to 3. All right, now let's go find our intercepts. The easier one to find usually is the y-intercept. Don't forget that the constant term represents your y-intercept. If for whatever reason you don't have a constant term, like if it's just not there, then that just means your y-intercept is 0. So what I'm going to do is I'm going to use formal notation. I'm going to say f of 0. That means I'm plugging 0 in for x. And the only thing that remains is the constant term -16. So my y-intercept is 0 comma -16. All right, I cleared the board a little bit so it's not so messy. Now, as far as your x-intercepts, don't forget that the way we do this is by taking the expression that defines your function and setting it equal to 0 and solving. Now, that is plugging 0 in for y. Remember, f of x represents y, so that's what we're doing, letting y be 0. Now, in order to factor this, you don't have to factor it, by the way. You can use a quadratic formula. But whatever you do, whether it's a quadratic formula or completing the square or by factoring, I hope you factor out a -2 first, okay? And that'll leave you with the following resulting trinomial, okay? And so now what I'll do is I will continue factoring. And it factors like this. Okay, and so what I'll do now is set each variable factor equal to 0, each variable factor. So x minus 4 is 0, or x minus 2 is 0. So then I'm getting two x-intercepts here, positive 4 or 2. I'll write them in ordered pair form. 4, 0 or 2, 0. These are your x-intercepts. All right, everybody, I think we have a lot here. Let's go to the x and y coordinate plane and plot this information. All right, everybody, this is what we have so far. We have our x-intercepts, we have our vertex, we have our y-intercept. I can go ahead and draw in the left branch here, best I can. I totally missed that y-intercept. Here, I'll just make the y-intercept extra big. Okay, so, okay, maybe I should do that over here. Let me just fix that for us. That was kind of embarrassing. All right, so there. It happened again. Okay. I think you get the idea. It goes through this, the y-axis right there. You can see my error. All right. Let's find an additional point using symmetry. Now, here we go. This is how it works. The mirrored image of the y-intercept. This is 3 units away from the AOS. 3 units, right? 1, 2, 3 units away from the AOS. 1, 2, 3. That means the mirrored image of the y-intercept will be the point that is 3 units away from the AOS on the opposite side. So if you go 3 units this way, you end up at 6, comma negative 16. Maybe about right there, eyeballing it. All right, and so now you can finish off the right branch. Oh my gosh, my parabola is a little bit embarrassing, but hopefully this looks like a U to you and not a V, right? Make sure it's a U-shaped, because V-shaped graphs belong to the family of absolute value functions. So this should be a U, this should be a parabola. All right, so this point here was found by using symmetry. All right, everybody, I hope you follow that example pretty well. Let us get the domain and the range for our function. So D for domain, R for range. Now, let's not forget, domain is read left to right, and we already said that it's always going to be all real numbers for the type of parabolas that you and I are studying. Basically, parabolas that open upward or downward. Now, the range, it goes down forever, and then the highest point is at the vertex, and the y value there is 2. So we'll put a bracket at 2. Okay? All right, everybody. Good job. Here's a summary of everything we discussed in this lesson. Now, the first form here that I'd like to highlight is standard form, or also what I call vertex form. And these are the steps that I would follow to graph a function when it's written in this form. Get the direction by looking at the leading coefficient. Determine your vertex. Now, you don't have to work for it when it's in this form. It's just h comma k. And your AOS always follows from that. Then find 2 additional points using symmetry. For the first point here, you have to plug something in for x. But plug something in, I recommend that is close to your AOS, close to your vertex. And then use symmetry to find the mirrored image of that point. When you have a function written in this form, get the direction by the leading coefficient. Find the vertex in the AOS. Now, there's 2 ways to find the vertex here. You can either complete the square in x or use the vertex formula, negative b over 2a. Find the x-intercepts and the y-intercept. Remember, the y-intercept is always your constant term. And the x-intercepts, you can find them by taking your function, setting it all equal to 0, and solve. You can use a quadratic formula or factoring or completing the square in order to solve for x. And then find 1 additional point using symmetry. Most of the time, that point that you're finding using symmetry will be the mirrored image of the y-intercept. All right, everybody, I hope this was a good summary for you. I hope you find this helpful. Good luck in graphing your quadratic functions.